This is a video for AQA Discrete Mathematics, Game Theory Section 1.2, where we're going to be considering stable solutions a little bit more and also the idea of dominance. Well, firstly, just a reminder about finding play-safe strategies. So if you look at the left-hand matrix, you remember that what we need to do is to work out the row minimum values. These are the worst case scenarios for player 1, and they are -2, -1 and -2, and then so for player 1 we want the maximum of those, so the maxi-min value -1. For player 2, look at the column maximum values, again the worst case scenario for player 2 because these are going to represent losses of 3, 4 and 2, and player 2 wants to minimize that potential loss, so we look at the column mini-max value, which is equal to 2, and that gives us a play-safe strategy of Q for player 1 and Z for player 2. Now the point that I want to make is that you'll see here that the row maxi-min is not equal to the column mini-max, so the row maxi-min is not equal to the column mini-max, and also the fact that the situation we have is that both players are going to think that it might be better to swap from their play-safe strategies. So if you look at player 1, for example, playing Q, player will look at that and say, well, I might be better off if I switch to R, which would give me 2. As long as, of course, player 2 doesn't also switch. Well, player 2 is looking at the same situation and saying, well, if I switch from Z to Y, I might suddenly gain 1 by going to the value in the matrix there, -1, indicating a gain of 1 to player 2. So both players have got some thought about possibly not staying with their play-safe strategy. If we went through the same exercise in the second one, I won't do it fully, but the row maxi-min is -1 and the column mini-max is also -1, giving us a play-safe strategy here of P and X. And if you consider that one, then player 1 is going to say, well, -1 is my best situation. There's no point me switching to Q or R because I'm going to be worse off. And player 2 looks at it and thinks also that if I switch to Y or Z, I'm also going to be worse off. So both players are going to stick with their play-safe strategy. Notice here that the row maxi-min is equal to the column mini-max. And we have what's called a stable situation, and for the other situation we have unstable. So that we have then that the stable situation exists if and only if the row maxi-min is equal to the column mini-max. So we say a stable solution exists if and only if we have the row maxi-min equaling the column mini-max, and if that is the case, then the saddle point, as it's referred to, which is the value of the game, is going to be the best situation for both players, so they're not going to move from that particular saddle point. So when we have a stable situation, both players will play safe and there's no point them switching from that. Okay, I now want to turn my attention to looking at the idea of dominance. And I just have a look at this situation and say, what would you do in Sunhill's situation? What advice could you give? Just spend a little bit of time looking at the different rows and deciding if there's any particular advice you could give. Now you may have come up with the idea that 3 is bigger than 2 and 1 is bigger than negative 2. So is there any point in Sunhill actually playing row R, or playing strategy R? This situation where the elements in a row are always bigger than the corresponding elements in another row is known as dominance. So what we say is that here row Q dominates row R. And if that is the case, then there's no point in effect R being there. So we say that strategy R is dominated by Q and should never play strategy R. So in effect that row is going to disappear, and we end up with the 3x2 game being reduced to a 2x2 game. So if the elements are always smaller than the outcomes in another row, then that row is dominated and you're never going to choose it as player 1. Turn that round for player 2, then we need to think about rows where the outcomes are always larger, and when that's the case, the second player is not going to choose those larger outcomes because that's going to be a larger loss to them. Let's try and look at that in a particular matrix. So here we have, just consider Joan here in this one. So you're looking at the rows. Is there any particular row in which the outcomes are always less than another row? And yes, we can see that in that case we have that P, the elements are always less than Q. So we can say that she's never going to play P, it's dominated by row Q. So in effect we can ignore row P. And if you look at Ellie, then we can look at that one and say, well, yeah, there is a situation where in row Z the elements are always larger than those in Y. So we can see that Z is dominated by Y. So she's not going to play Z. So we've reduced that game from a 3x3 to a 3x2. So you can say, is there a stable solution for this? Well, we go through and work out the row minimum. So the row minimum are 3. So just put the title in here, row min are 3 and -1. So the maximum min value is 3, and the column maximum values are 5 and 4. So here we have a situation where we have the row maxi-min is not equal to the column mini-max, and therefore this is not stable. So if it's not stable, there's some advantage in switching the strategies. And we have then what's called a mixed strategy. So they're going to vary what they do. Instead of playing the play safe strategy all the time, we might switch. And now it's this mixed strategy which then becomes the central idea of game theory and trying to decide which strategies you should play and how often to maximize your outcome. And that we will consider in the next video. So optimum mix strategies is to be considered in the next video 1.3.